Thank you, Sri, for that kind introduction. I hope that the talk lives up to the intro. What I wanted to say today is I think layout is going to be really important to how we program current and future architectures. And so I'm really excited to share with you some work from my group over the last 8 or 9 years. And I think it's very mainline in the context of the subject matter for this workshop. I have a lot of collaborators. I'd like to make some acknowledgments here. So first of all, I have 6 PhD students. One of them, Amr, is here in the audience, and I'm going to be talking about some of Amr's work at the end of the talk. I'm also going to be talking about work from some of my former PhD students and my long-term collaborators at Lawrence Berkeley Lab. And I have some new collaborators at AMD, and so Sangeeta's here today, and so this is also sort of factoring in my thinking about these issues. And Cosmo Noencia was on sabbatical last year at Utah, and we're going to talk about some of his work as well. Okay, so we're here because this idea of tile programming abstractions has become really popular. And it's been popularized by Triton, in particular, dating back to this 2019 paper. And now we're seeing a lot of other systems. Probably the most other common system is cuTile. And what do they get for you? They do 2 things. They raise the level of abstraction for the programmer. But more importantly, and that's definitely been Triton's priority, they provide some signals to the compiler. They tell the compiler that this is some object that you can move around at particular points in the computation. And just to, I don't know if you can see it, but the cuTile programming model is in the slide. This is like the home page for cuTile. And you just see that you load, this is just a vector add, and you load the 2 inputs. And you do an add. You don't have to have a loop describing the add. You just say, I'm going to add these 2 vectors. And then you do a store. And so you can see cuTile's really prioritize raising the level of abstraction for programmers. OK, and this is some Triton code from the repository. And I color-coded this, and we'll come back to this later in the talk. So there's the green box is the thread tile. So you're describing the thread tile, and for that's for a thread block, and it's actually a pretty complicated formula here because they're trying to do something to, I believe, eliminate bank conflicts, and so they have this complicated formula. And then we're also tiling the inputs and the output, and we're connecting them to the thread layout. And the pink is so the color coding is green is computation layout, and pink is data layout. Okay, so although we're all here at an array programming conference, the kinds of ideas that led to Triton are very old. They have built up over the years, and so I'm just going to take a minute, because I don't want to claim these things are my ideas either. I want to take a minute to look at the history, and I'm old enough to have lived all of this history in my career, so I remember it when it was happening. And so just tiling dates back to work by Michael Wolff, and the first paper that I could find is from 1987. And I want to kind of point out why this was very unique. So a lot of the research on iteration, so the idea is tiling is an iteration space reordering. You're changing the order in which a loop nest executes, in which the iterations of a loop nest execute, to change the memory access pattern. So you're not changing the layout to change the memory access pattern. You're changing the iteration order to affect the memory access pattern. And originally, iteration space reordering transformations were focused on exposing parallelism, improving parallelism. And so this is a case where it's focused on improving locality. And so Michael Wolff had the first work on tiling, and then a different Michael Wolff with Monica Lamb did some pretty seminal work on coming up with a locality optimizing algorithm. So that's the origins of this work. There are a very large number of compilers for distributed memory architectures in the 1990s, as well as a lot of different distributed memory architectures in the 1990s. And so I'm just listing a few of these things. The high-performance Fortran was a standard that was created in the 1990s. And the key idea with high-performance Fortran was that a programmer described how the data is partitioned across nodes in a cluster, in a distributed system. And from that data layout description, the compiler could generate the code. And there was a notion of owner computes. You said, okay, if I own this data element, then I'm the one that's going to compute the output. I'm going to gather the data from other nodes. And so most of the time, the layout was a tile. And that you were describing for the computations of the day. In the 2000s, there was a refresh on distributed memory compilers. DARPA had a program called High Productivity Computing System, and it funded a bunch of computer vendors, IBM Sun and Cray, to create new programming languages. You probably heard of Chapel, which is still very active today. You may have heard of X10 as well. There was also one from Sun called Fortress at the same time. And so we already had this integration with these distributed memory compilers. We already had this integration of layout with the compiler. I also want to point out something maybe forgotten, a little bit forgotten, this work on hierarchically tiled arrays. This is a collaboration between the X10 team at IBM and David Padua at Illinois and some other folks. And the idea was to be able to express at a very high level hierarchical tiles and then have the underlying system be able to address the indexing, come up with the indexing expressions that represented that. And this is a paper, the key paper from that work, Programming for Parallelism and Locality with Hierarchically Tiled Arrays, and that parallelism was across nodes. That was a distributed memory abstraction. Okay, and I've done a lot of work on structured grid computations. You're going to hear about it quite a bit today. Here are some domain-specific frameworks that realized, if I have the data in these sort of contiguous tiles, then I can get better performance. And I'm going to come back to that real soon. There are tiled data layouts for distributed memory. These are relatively recent. Distal is for distributed tensors, but it's a long paper in a series of papers from Alex Akin's group and others on how you express data layout. And then finally, towards the end of the talk, I'm going to talk about tiled data layout for matrix processors, things that were particularly designed to target matrix processors. Okay, so here's my talk. Now that you've had the history, you have the context, my talk has 3 parts. I'm going to talk about a project called BrickLib, and the idea is I'll tell you what the idea is, but the way to think about it is the use of tiles as your data layout has all sorts of benefits to reducing data movement. The second part of the talk is about Lego. That's Amar's work. It's a standalone hierarchical data and thread layout description that's open source. And then I'm going to end with a description of where's architecture going. I go to a lot of meetings where we talk about this sort of thing, and a call to action for the community as to what we should all be doing. Oops. Okay, so part 1, BrickLib and how tile data layout reduces data movement. So this is kind of the idea slide here. So the brick data layout is designed around a unit of data, a brick, and it's also a unit of parallel work. And so the node, at a given node in a distributed system, the layout for that node is a collection of bricks. And if things are more hierarchical, there's a collection of bricks at each level of the hierarchy. And one of the goals of this project, and one benefit that you can get from an approach like this, is you can achieve performance portability. Performance portability refers to being able to get good performance on the same piece of code across architectures. And because you have a unit of work and data, you can adjust the size of that unit or the size of the collection of those units to match the architecture and what the architecture can support. So I'll probably say this a bunch of times, but what do you get? You speed up data movement from this abstraction. You eliminate some unnecessary data movement. And it also helps you in a distributed system to reduce the amount of reorganization of data that you need to do to communicate. So it's improved strong scaling as a result. Okay, so this is a slide you need to pay attention to. It's the key to everything. BrickLib uses this brick as a key abstraction. And so a brick is a small subdomain. The sweet spot is often 8 by 8 by 8 elements. And that's very conveniently like the size of a page on an Intel system. It's, it's a really nice, it fits in L2, et cetera, et cetera. So each brick is stored in contiguous memory. So it's a 3D object, but it's stored in contiguous memory. So everything in a brick is nearby. This picture is showing you a global domain for a distributed system, and we're highlighting this one little colored section in that global domain. So this picture, the bottom center, is the subdomain that's mapped to a node. Okay, and for convenience of presentation, everything's 2D. So it's a 2D object in this picture. It gets a lot worse when it gets a lot more problematic when it's elevated to 3D. Okay, so each brick is represented by a color. And internally, you have the domain that's mapped to this node. Externally, you have ghost bricks that represent neighboring data from neighboring nodes that you may locally compute. You need to locally store at the very least. And so the layout is that each one of these colors, you can see, this is memory. And each one of these colors is stored as a stream of contiguous data. And whereas if you stored it in a two-dimensional array in row major array layout, which is the common layout for C code, or that you would have these big strides. So the colors would be spread across a bunch of cache lines. When you get to 3D, a bunch of pages. And so the other thing that's really interesting about this layout is I can move these bricks around so that I can order them so that I can communicate, and I don't have to pack the data to communicate. So for example, when you're doing a stencil computation, you'll take, for example, the row of bricks at the top, and you'll communicate them to some neighbor above you. And if you look over here, you can see that all those colors are adjacent. So I just point to a big block of data, and I send it. I don't have to reorganize the data to make it contiguous. But for example, this block on the right, that's not contiguous at all in a conventional architecture, because it's striding by, the domain, some big chunk of the domain. And I can send data to the right of me, and again, I can lay those bricks out so that all of that data is contiguous. And there's some fancy memory mapping in case something needs to be sent in multiple groups to be able to have it be in contiguous addresses. And this is really important because in stencil computation, you have to reorganize the data on chip, on node, in order to move it to your neighbors. And you spend a bunch of local data movement doing that. But with BrickLib, you don't have to do that. You just lay the bricks out in the order that you want to communicate them. OK, so that's bricks in a nutshell. And now we'll get a little bit more concrete and look at some of the results. This is a 2D 5-point stencil expressed in BrickLib. And so this looks like normal Python code. And there's one difference, which is that I have a brick associated with the computation that I want to do. And if you know about, if you optimize stencil code, you're going to go off the end of the brick in all dimension. And the code generator knows that and is reaching into other bricks in order to generate the code. This is all Python-based. And I think that's all I want to say. OK, and so the abstraction, the bricks are laid out in some order. The abstraction is that I have some indirection that allows me to say where the next brick is. And that means that I can have a physical layout. I talked about the communication. I can have a physical layout that's different from the logical layout and use this indirection just to resolve those things. And I've already made this point, but there's also a way of specifying the communication in the brick library and the layout and that is used for the bricks involved in communication. And that allows us to just send big chunks of data to our neighbors without having to do any packing. OK, so that's the key ideas in BrickLib. And this is just some very recent results. I spent a lot of time looking at roofline graphs. I don't know if everybody does, so I'll just very briefly tell you what these graphs mean. Your performance is limited by the hardware memory bandwidth that it can deliver and the peak compute performance. And where you are on, so the diagonal line is the memory bandwidth, and then you reach a certain point where you saturate, you have enough arithmetic intensity to keep the processors, the compute processors busy, and then you flatten out in this horizontal line. And so this project targeted 3 different architectures associated with the DOE's exascale computing project. So we're showing an A100, an MI250X, and Intel PVC. These are different GPU architectures. And the reason that for the kind of triangular shaped set of graphs is that the first one is the A100, and the programming model is either CUDA, HIP, or SYCL. And when you get to the AMD, it only supports HIP and SYCL, and when you get to the Intel, it just supports SYCL. And so that's why it looks like this. And the bricks cogen are the yellow boxes. The box-shaped stencils are the boxes. The plus signs, which are a little bit over, they're a little harder to see, are the star-shaped stencils. And in all cases, the bricks, so we compare just a general tiled, very aggressively tiled array-based implementation, the array-based implementation using the same code generator as BrickLib, and then the BrickLib code generator. And so we were trying to isolate the benefits of the code generator versus the brick data layout. And so in all cases, you can see that The yellow boxes is the farthest to the right, which means it's getting the most arithmetic intensity. And we're very close to roofline for a stencil computation. And then this is just to show that it isn't just a bunch of stencils. This is implementing a geometric multigrid using BrickLib and across the 3 architectures and comparing it to the HP-GMG benchmark, which is the standard benchmark for geometric multigrid. And so we can see that that we're getting high performance gain over HP-GMG, which does not use a brick, and that we're continuing to scale. And then the last piece of work on BrickLib is applying bricks to deep learning. And I want to spend a little bit of time on this slide to explain what we're doing. The picture at the top kind of shows it. We have 4-dimensional bricks. And what we're trying to do is, sure, you can fuse across layers and get reuse across layers, and all the libraries and compilers and everything else will compose fuse a convolution with ARRAY'. But people can't fuse multiple convolution because there's a dependence. And so what we're doing here is we're doing an operator at a time on just the brick, computing the partial result on just the brick. And this picture at the top, you can see the brick is a little bit bigger and it gets smaller and smaller because you need to compute the things around the edges when you're doing a convolution in order to have the input that you're going to need downstream. And so there's in this paper that appeared in ICPP 24, there's a very clever memoization of the partial results because that area around the outside the ghost zone may be needed by different elements. So the same result that you produce may be used in multiple places. And so there's a memoization of the result and a synchronization to figure out whether the result is available or whether you should calculate it. And we call this merged execution because we're not fusing the convolution, the multiple convolutions. What we're doing is we're executing one on a brick, and then we're executing the next one, one that produces the output for the next one. Then we're taking that output and doing the next brick, and everything's still in L2 cache. And so we're getting that reuse simply by doing one brick at a time. We've chosen that smaller size. And so the idea of that is the experiment that I'm going to describe is that the computation you run on the brick is you can just use a code generator, whatever deep learning code generator you have for the brick level computation, and then the framework is doing the stuff around the edges, being able to doing this memoization and keeping track of the overall results on this bricked implementation. And so we use a lot of different code generators. TVM produces the best results, the final bar is what you get from merged execution. So you get a little bit of a win beyond what all these deep learning systems are doing. Okay, so that's the first part of the talk, and now I'm going to spend some time talking about Amr's work on Lego, which is a hierarchical layout description. And again, here's what the idea is. So the idea of Lego is you're describing the layout for either data or threads hierarchically. And it's the same way. We think it's productive for the programmer because it's the same way it's mapped to the hardware. And it's a standalone description. and implementation that's open source. So you can attach it to anything. And we have attached it to a bunch of things. And it's supported by a grammar specification to make sure that, it gives you a correct layout. The result is you don't have to express explicit strides, you don't have to be tied to a particular tool, and you're not constrained by the domain. It can be, there doesn't have to be a deep learning thing. Because it's standalone and open source, you can integrate with all sorts of things. And it's generalized to support user-specified layouts, which I'll show an example. Okay, so this is kind of the spectrum of how you generate code for tensor cores. You know, you can write extremely low-level code or very low-level CUDA code. You can use Triton or other DSLs, and there you can elevate that by having a layout-based code description. And so the work in I mentioned this before in for Chris Cheka's work in Qt, and that's part of this graphene paper that I'm going to mention. And then linear layout, that's a very recent paper from OpenAI. So Lego's trying to be a little bit more productive than all of those things in the space of generating hierarchical layouts for GPUs and particularly targeting tensor core code generation. Okay, so we're back to this Triton example from the beginning. This is the same code, now with a little bit more annotation, the green and pink. And then there's also this blue box here. And that's where we have to update the stride across the block. And so this is where the code has explicit strides. So on the right-hand side, we've implemented in Lego the same thing. We have an integration with Triton. So it's going to produce identical code, but it's going to get there in a different way. So the programmer is expressing the yellow the green and pink boxes at the top, the thread layout, and the data layout. And we use this Jinja notation to say, here's some things that need to be filled in, and we're mapping them. So anything in the curly braces is going to be replaced by the Lego system. So, we end up with the same code from expressing this layout, but we didn't have to think about strides, and we were able to describe things in a little bit more hierarchical, intuitive way. Okay, so here's a comparison with other layout description. So linear layout uses a binary matrix to describe the layout. Qt and Graphene have a stride-based representation, and Lego has this hierarchical or recursive description. Here's an example from the Graphene paper. Okay, and this is a strided layout in 2 dimensions. So the colors, anything with the same color is part of the same tile. And so in Qt and Graphene, the top row is the tile sizes, the bottom row is the strides. And so we end up with these tiles of size 2 there are 2 of them in a row, and they're also skipping in the vertical dimension as well. And so down here, you say that there's a stride of 4 to the right horizontally and a stride of 16 vertically. So this is the expression of that picture. In Lego, you describe it as a permutation of the dimension. There are 2 by 2 by 2. I'm sorry. There are 2 element tiles, and we've just permuted the order of the dimension. There are other restrictions on linear layout. Linear expressions, sizes of power of 2, Qt and Graphene are strided rectangular regions. In Lego, we have a space for user-defined functions, so you can express any kind of arbitrary bijective mapping. And that can be done at runtime. That can then be resolved at runtime. Okay. I think I'm going to kind of go fast through this slide because I want to get to the end of the talk. But this is a description of the building blocks. And so we're describing the original layout with this group by. We're then tiling it with order by to produce this four-dimensional 2x2 by 3x3 grid. And then we actually introduce the anti-diagonal, which is an arbitrary user-defined bijective mapping in the last box. And yeah, so we flatten the logical description and we reverse that to unflatten into the physical location. And there are other versions of the other things beyond bijective layouts that the paper talks about supporting. Okay, so Lego is a standalone algebra. We've integrated into Triton, as you saw, into just arbitrary CUDA program, and into the MLIR compiler. And these are a few results. Using Lego as a front end to Triton, we get effectively the same performance as Triton, and for certain benchmarks, we get improved performance over PyTorch with cuBLAS. And the other thing that's kind of interesting from these pictures, and these are different problem sizes, is we have these 4 different matrix multiplies where we're transposing the 2 inputs and the output. All of that's done with layout. We have the exact same code, and we just change the layout, and we can produce a benchmark. So if you wanted to be able to do that, you could. We use it not just for tensor core code generation, and not just for matrix multiply, but just we're showing that you can formulate thread coarsening as a layout problem. And you need to change the thread and block decomposition and the data layout, and then you end up automatically generating the index expression. And then the anti-diagonal is used to eliminate that complex. Okay, so that takes me, I think I'm going to finish just in time, to the last part. I want to talk about what's happening in the field, what's happening with computer architecture right now, what we have to look forward to, what the challenges are ahead. So there's a paper by Gordon Bell that introduces Bell's law. I guess he was unhappy that Moore got all the attention, and he has his own law. And the idea is that a new computer class forms roughly every decade. And it creates a new industry. It also creates architectures that are cheaper, faster, or more capable. And so in order to, and I have a talk where I go through from the 80s onward, and I go through my whole career, and it just describes everything on the software side, everything that I did, that I worked, the kinds of problems that I worked on. There is a period of observing that there's some technology trend coming. And then there's a new architecture or a new class of architecture that's designed around that technology trend. And then, sadly, the programming system always follows. It takes a while to catch up. And then there's a period of assessment. And so where are we right now? It's clearly AI everywhere, but what does that mean to architecture? Let me also make this point. I was on this working group, task force for SciAm on the future of computational science. And I had 2 things from this that I'd like to talk about. One of them is this bottom quote, which is saying, we're used to anticipating these technology trends and designing around them and building new software. But right now we have no idea what's coming. And there isn't like one thing right now. There's a lot of different things happening. And I'm going to try to unify that a little bit. And then the other thing, which was a quote during the task force discussion that really illuminated things for me. For all these years where we had a supercomputer with a CPU, and a GPU on each node, or a collection of GPUs on each node, we always called those heterogeneous systems. But how much work did we do on the CPU, right? The CPU was the orchestrator, the GPU was doing all the work. And so somebody said, these are homogeneous clusters of heterogeneous nodes. They're not the heterogeneous systems that we're going to see, coming down the line. Okay, so this is my take on where architecture is headed and therefore where software needs to head. So they're going to, architectures, and we already see this today, are going to be three things. They're going to be heterogeneous in all sorts of ways. They're going to be hierarchical, they already are. And they're going to be asynchronous. And so we can have heterogeneity at very coarse grain and very fine grain. We can have an AI supercomputing system coupled with an AI system at the very coarse grain, and that, or a supercomputer coupled with a quantum computer or something. We have heterogeneity at the chiplet level. Chiplets are becoming more prominent because it's a way to build reliable hardware and squash a lot of compute capability into a system. And sometimes it's a way to have specialized chiplets, so you can, domain-specific chiplets that you can integrate with a more conventional system. And so the color here is just to say, the purples are the whatever the main processor is, and then the other colors are some other kind of chiplet. And the hierarchical, we already see it in a GPU, for example, today, or in any kind of, in other kinds of system. You have a matrix processor, thread block, a GPU, multi-GPU node, and then this heterogeneous, homogeneous cluster of heterogeneous nodes. And then the asynchrony, we are used to that in distributed computing. But what we have now is very fine-grained asynchronous nodes. And so now we have to worry about very efficient interactions between processing units and memory. And we have to do that at a very fine grain. We also have these tile architectures. One of my students has done a bunch of work mapping geometric multigrid to Cerebras, which is a wafer scale tiled architecture. And so these are all the things that are going on in the hardware space. So what do we do about it as software people? So the software needs to partition the computation between the different units. Where should this work be done? What's the right functional unit to do this work? And then it has to asynchronously marshal the data around to either store it or to the next place in the computation. And I also want to say that this is unlike this ecosystem that we are building right now is unlike previous decades. I've been through a lot of decades of the Bell's Law, and this is very different. In the past, something like MPI, for example, was a community effort. It was a partnership between the federal government, academia, and industry. And it was driven by the community. The results were always open source. And the applications were coming from the scientific grand challenges, like how do we, predict the weather or whatever. today's architectures, the programming frameworks are being built in industry. And the amount of resources that industry has compared to what the federal government has and what the academics can muster is just orders of magnitude different. And what I'm concerned about is a lot of the things that are going to give you good performance are proprietary, all the pieces of software. And not only can the academics not see them, the other thing is everybody has to build that. All this asynchrony, everybody has to build that. And so for all the gobs of money being thrown at building programming systems for deep learning, there's a lot of duplication of effort across industry. And and meanwhile, the target application is deep learning, and so maybe your linear algebra algorithm can run really fast, even if it's not deep learning. But there are plenty of things that look very different, and will need a different kind of hardware to support them. So this is kind of my concern, and I just kind of want to raise awareness of this, and also just for all the industry folks out there in the audience, and every industry person that I can find, open source and working with academics can really help the community move forward, can help support the academics in a time where things are a little bit strange, and that takes me to my last slide. So this is a really exciting time to be doing to be building compiler technology and runtime technology too. And there is just this profound architectural change, and it's dominated by this investment in deep learning. And my whole career, no one ever had any money for compiler writers. There was never any money. You had to do enough to get the hardware to look pretty good, except you could do a lot of that by really low-level manual coding and building libraries. There was never enough money. Now there's just gobs of money building compilers. And it's really good for those, any of you who are grad students and you're looking to find work when you get out. There's lots of work, because this hardware, all the things that are happening in hardware, they need software for them. So it's a great time. It's really exciting. This talk has been about data layout. I think data layout is essential to performance. And as we start thinking about asynchronous data movement, we're really going to need to be able to get a handle on what the data is. We've seen with these GPU-based data layouts that you need to express both the parallelism and how you organize the data and how it relates to the parallelism, the thread layout. And eventually we're going to have to manage this fine-grained asynchronous data flow model that's emerging. Okay, what's next for me? I didn't talk about other work that I've done in the last 8 or 9 years. All very related, all about data movement in some way or other, on sparse tensor code generation, on mixed precision, on sparsified solvers, things where you're reducing the amount of data, the size of the data, so that you don't have to move so much. And probably some other stuff I'm leaving off. And where I'm moving is, on the computational science side, moving into something called hash bricks. So the bricks are still dense, but now we're doing adaptive mesh refinement. So we have different levels some parts of the data will participate in different levels, deeper levels or more shallow levels, and then some things will not be represented at all. So the bricks, the individual bricks are still dense, but the overall grid structure is sparse. And that's producing a bunch of challenges, but we think it's a very promising direction. And doing some work, one of my students, the one who's been working on mapping to Cerebrus, is looking at how to generate code that combines data layout and asynchronous execution. And also Amr is working on that at the tensor core level, how you deal with the tensor core async and memory access asynchrony. So that's all I have, and I think I finished on time. Well, not really, but close. Thank you all for your attention.
We have about 15 minutes for questions.
Oh. Oh, maybe there was a, maybe okay, I got it. Okay, great.
Right. So, questions from the audience?
Yes? Oh, I'm sorry, I'll let you run it.
Thanks for the really interesting talk. I guess you kind of touched on it at the end, but I was really curious when you mentioned both like indirection and this kind of like runtime injection for like dynamic layouts. So do you think sparsity, and specifically like less structured sparsity, like block sparsity or fully unstructured sparsity, do you think that the current abstractions for thinking about layout, which are very like static affine dense, are useful, or do you think that we really need to think about layout in a different way, or in like a more like runtime metadata centric way?
Yeah, that's a really good question. So let me say sort of two answers. There's a yes part, which is the block, to the whatever extent you have a block structured layout, that part can be specified in the same way. Or if it's a little bit sparse, you can do that in the same way. For example, the hash break, some part is dense, right? But the overall structure is sparse, and we still can get some leverage from the dense mechanism. I have done a lot of work on specifying layouts in the sparse case. We're definitely stronger when you have dense blocks. And otherwise, there's a lot of work on specifying sparse layouts, and there will continue to be. And I think that, to me, there's like a hierarchy there where there's the parts that you can specify densely, and there's the hierarchy that maps to the hardware. And I think some of the ideas translate and some don't.
Hey, thanks, Mary. Great talk. So you, at the end, you sort of alluded to like we're going to have this crazy like asynchronous, communication to deal with coming up. But from what I'm seeing is it's already here. There's already crazy synchronization constructs. And if you remember, even more than 10 years ago when I was at Utah and doing my master's thesis, we showed that communication was really difficult even on existing systems. And you're doing it on AMD and Intel now. And you didn't really necessarily talk about kind of the correctness issues around synchronization. And I'm just wondering what your experience has been with that. Is that needed in the community to look into that? Or, if you could just comment on that.
I cheekily said, I want the code to run really fast, and I'll let the rest of the people here worry about if it's correct. But absolutely. Sometimes you don't have the kinds of synchronization you guys think about. You don't get that with, array-based, there's certain kinds of computations that don't trigger those kinds of synchronization errors. And I think that that a lot of times people were using GPUs in a particular way where they weren't having problems with that, or even sometimes things would magically work, but they were really not correct. I think we're going to see a lot more of that. So even though the problems were already there, partially because of the design of the hardware, now the hardware is much more asynchronous. And even just like a tensor core, it's like, that's a very different abstraction from what you're used to thinking about for a GPU. So I think we're going to see a lot more of it. You're absolutely right. Especially you guys who think about like trying to find the correctness error, that was always there and will continue to be so. But I just think that when you start thinking about your application as something that fits on a tile, that each tile is doing a piece of the computation, and you have to, completely rethink how you implement that code, I think that's going to trigger a bunch of more challenges.
Cool, thank you.
Thanks for that. I'm curious your thoughts on unified memory architectures where CPUs and GPUs share the same memory. And it seems to be a trend. Apple Silicon, there's AMD chips, there's a lot of embedded chips. Do you think there are interesting opportunities there, or do you think this is going to be something we see more of? Are there things that you envision doing differently in your system because of those?
Yeah, I'll just say a little bit. I did actually, in my heterogeneous, I had APUs as an example, and I forgot to mention it. But one thing that people have found, so GPUs for a long time have had this unified address space, even if it wasn't real. It was an abstraction for the programmer. And so sometimes you would find yourself with some replication across the CPU and the GPU. What people have found is, and if you had an application where the data didn't fit on the GPU, and this has been a problem with GPUs, they don't hold a lot of data, relative to what you could do on a CPU node. So the APU moves the needle a bit in terms of, if you're right on the edge, you now have a way of having not having this replication of the abstraction across the CPU and the GPU. So you can actually solve bigger problem. That's one of the things that, there's a paper from the Lawrence Livermore folks on the MI250X from a couple of years ago that does a study on this. So it is going to be better than what you have in a GPU. So if you have a problem and it doesn't fit on the GPU, it is going to be a little bit of a better performing abstraction. How much are people going to want to share those things? I don't know. That's a really interesting, I think the applications aren't necessarily there because people built the applications for the previous model. And so I think we'll see what happens.
Thanks for the talk. I have a sort of a spontaneous question composed of the last two, though. Picking up on your correctness, your jokingly correctness is other people's problem. It seems like one of the things that's happening is like both with unified memory or like the appearance of unified memory, like all the shared memory, like distributed shared memory, and communications. I think one thing that I'm curious what your perspective is it feels like some amount of correctness becomes more the job of the performance people, because the only way to produce really good performance now is to write really complicated programs. For example, like everyone's doing these fancy like one-sided RDMA, like in the spirit of lock-free programming style, acquire release fanciness, where it's like, oh, I wrote to some shared memory address that is actually like physically replicated across all the machines, but now I have unified memory. So I think maybe that's one question that I have is, do you see a difference in the doing performance work in this era? Because I've actually seen performance people asking for correctness for the first time, and given that I was like a verification person, became a performance person, this is crazy to me. So I wonder if you have any thoughts just from your perspective and your historical view on the field.
Yeah, I would. You're absolutely right. Like people do things for the sake of performance, and sometimes they're not guaranteed to work, but they look like they're working, and so they're satisfied, right? And how do you prove that? I think that this may be where AI and the formal methods folks come together and really try to address this, because on top of everything else, Claude's going to create that code too, right? And it's going to find some code like that and create that code too. So I think this is I made my pitch to the programming system, to the compiler folks and the runtime folks, but I'll make it to the correctness folks too. This is a great time for you guys. And I think you have some tools where you can make things, you can do things a little bit more automatically just by virtue of having AI support. This is just my very outsider view of things. And we've seen some experiments in our own work where we're able to prove correctness of something that we wouldn't have been able to in the past. I think it's a golden age for you. I do think people are going to write that code, and especially if it speeds up something really critical, people are going to write that code. So we would love to provide abstractions so they don't have to. But we also need to make sure that the code is correct, and we need to make sure that the AI-generated code is correct as well, especially when it looks like that.
Hi, Mary. In HPC, of course, has been thinking about these problems for a very long time, but the architectural trends around caching about heterogeneity, they're going to hit other parts of computing as well. So like if you're thinking about application level programming, you're thinking about systems code, what should people outside HPC learn from HPC's experience of how to deal with these hardware trends?
Yeah, so what you're saying is a lot of people are going to have to be writing heterogeneous code, and not just for performance reasons.
You guys have figured it out, so.
Well, we haven't figured it out, and you know who's probably figured it out more is more in the embedded space. You know, your phone, whoever programs your phone, probably has some abstractions that, you know, they're fast enough and they work, and so. So I don't know. I don't think we, you know, as I said, in HPC we were it was homogeneous nodes, you know, heterogeneous nodes, but homogeneous clusters. And so I just saw a talk by Bill Gropp last week because he celebrated his 70th birthday, and he was talking about a very simple problem that everybody has, which is you have a cluster made up of different, you know, nodes, maybe different generation, and each one of them has different capability. It has different numbers of cores or something like that. No one's figured out how to run a program on that and get good performance. We only know how to think about homogeneous systems. He had tons and tons of data showing this. That was very fascinating. And it's just the most basic kind of heterogeneity. Now imagine you have a data center, you spend $1 gazillion, and you want to add some more nodes to it. Well, you're not going to add the thing you added, you know, you built 5 years ago or whatever. You're going to add something new. And now you have a cluster that's GPUs that look different. I mean, we're going to have this problem in space.
So no help.
No help.
Yeah, thanks, Mary, for a great talk and your leadership through the field. I love the historical perspective going back to Wolf. I find myself pointing people at that paper over and over. At that time, Wolf was sort of concurrent with systolic algorithms, right?
Yeah.
They had just come out before, and both Wolf and Lyserson and Kung were exploiting kind of symmetries within a matrix multiply to get locality. So if you carry through the Lyserson track, there's a field of VLSI algorithms, you know, that's carried through today to communication avoiding algorithms.
Sure.
There was also an element of topology. You know, people were talking about hypercubes and arrays, and that carries through today, you know, into different network fabrics, you know, Dragonfly and beyond. So as we're optimizing for layout, I think we're assuming a topology, like what talks to what, the physical organization of the machine. And I wonder if there's a way to play kind of a three-dimensional chess game like, you know, Mr. Spock on Star Trek. You know, you're sort of working on layout at one level. Well, there's a simultaneous game around topology that we have to think about. And how do you bring topology into your thinking about programming abstractions and optimization methods?
Yeah, I think that's a really good point. I think there's a partial answer, which is, what do we do in our work and the other work? We were composing the thread layout with a data layout. And now you're talking about the topology. And I don't think it's going to be and I'm thinking about the Cerebrus architecture because you just go, it's just a 2D. Yeah. And so so, you know, if you got data over here and you need to get it over here, like, you're doomed, right? And so there's both the kinds of abstractions that we're thinking about. They would stop you from they would stop you if you composed a topology onto that. They might stop you, and that's probably not the right thing. What you really want is to understand if it's bad, right? You want to have some kind of model of, okay, with this topology, this has this result. And I think that's doable. Actually, Amr can think about that. I think that's doable because you want to be able to say, I have this north, south, east, west configuration, or I have, the fanciest, the Dragonfly network. I have, you want to be able to say, don't use this algorithm on this hardware. I think that's the result, or this is a better algorithm than that on this hardware. And I think that's a really good point. Not something I thought of, though.
I don't know whether we are. Okay, this is a quick one. Again, when you go through generations of hardware evolution, wire-to-compute disparity has become really shabby. I mean, right now it takes very little. I mean, a register-to-register movement is far more efficient than register to the next level of memory hierarchy. And if you had to cross over CoWoS layers, it is even insidious. So there was an era when things like Tensilica used to be around, if you remember, programmable hardware, where you actually make the hardware itself morph over time. I don't think there is an appetite for that because muxes impose a dead cost. Have you heard anything remaining in that space where runtime hardware might be, like in the topology question also?
That's probably for somebody else in the room to answer,
yeah,
but
there
it's
might
a really
be
good
some
point.
macro level reconfiguration that might be exposed more than through just the
other
instruction
than FPGAs
sets.
or something very
FPGAs
configurable.
yeah, but there's a wire cost problem. Yeah.
Yeah.
Anyway, I was thinking if anybody has awareness of there being a discussion in that space. That's all. Yeah.
Is there a question? Yeah.
Thank you for the talk. Most of the abstractions that you have introduced here are data flow centric. So can you comment a little bit about how we should think about control flow in this kind of space?
What was what centric? There most of the abstractions?
Most of them are data centric or data flow
Oh
centric.
yeah, data. Yes.
So how should we think about control flow in this space? Or control flow abstractions in general?
I mean, at a very, we think about it at a very coarse grain, and then it isn't so important. I guess if you're thinking about it like at the, like within a function or something like,
Yeah.
at that very fine grain within a function. Gosh, I don't have a good answer for you. I think that those are that you rely on for the control flow at that fine grain, you would probably rely on the underlying code generator because it's not going to introduce. It probably isn't going to introduce a bunch of data movement, or it's a piece of computation that's not really going to get you to that very highest level of performance.
I feel like the cheeky answer is control flow is bad. A lot of these things, you want a program that is in data flow mode because control is expensive. Like a lot of the control constructors, or beyond thread level masking or something. When in general, if you have these big forks, it's bad for your program. At least in the ostensibly HP, people have the dense compute that you want to keep computing as long as possible. And if you change layout, for example, if you have a dynamic shape, or you need to go back to the host, it's not great for your program. At least that's my cheeky answer.
Thank you.
Okay, let's take a last question.
The BrickLib stuff is really cool, and I'm wondering, can you explain ways of automatically choosing brick sizes?
Yeah.
For example, if you have the same code running on a supercomputer versus a phone versus a personal laptop versus something else, have you explored that space, and what was your experience?
Sort of specifically, we have looked at cross architectures and changed the brick size, and cross applications too. You can tune the brick size for the application as well. So certain, and you can even have irregular brick sizes. We've tried all those things, and that's actually the beauty of the design because it doesn't care what the brick size is.
Makes sense.
Everything will work if you change the brick size. It's just a parameter to the mapping. And one of the things that we discovered, some of these stencils, in a longer version of this talk, I show a very complex stencil, build a big data flow graph to generate the code for that computation, and you end up needing much smaller brick sizes because you have a bunch of related data that you want to store, you want to co-locate, and so you end up having much smaller bricks for that computation. So yes, we have done that, not at the level that you mean, but the abstraction allows you to do that.
But no like automatic heuristics.
Well, I mean, we do
or
auto-tuning.
Auto-tuning,
you know,
okay, makes sense. Okay, cool. Thank you.
Thank you all. Great audience.